Good day. My name is Stephen Griffiths, and I work at the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. And I have been a colleague of Dr. Suki Manabe for many, many years. And we are honored here today to talk with Suki about the recent Nobel Prize that he received for physics. He shared that prize with Klaus from Germany and with Giorgio Parisi from Italy. And both Klaus and Suki's work touched upon the climate of the Earth, the atmosphere, the oceans, the modeling of that climate. And I'm also representing the AGU. I am the chief editor of a journal called the James, which is the Journal of Advances in Modeling Earth Systems. And this is an AGU interview. Suki, of course, has been a member of the AGU for many years, longer than I've been alive. And I would like to summarize a bit, to introduce this interview, summarize a bit of the work that Suki has done by quoting from a recent article in Scientific American written by Gavin Schmidt. Gavin is a senior scientist at NASA. He's the director of the NASA Goddard Institute for Space Studies in New York City. So Gavin says that these two scientists, Hasselblad and Manabe, are representative of two main themes in climate science. Number one, the development of predictive, physically based climate models, and number two, the detection and attribution of climate changes. Together, these advances allowed us to understand climate changes of recent past and make skillful predictions of climate's future. So, to continue with reading from Gavin, I'd like to introduce the first question that I'd like to ask to Dr. Manabe. One of your major contributions to climate research has been very fundamental, Dr. Manabe. It deals with the atmospheric radiation and the response to an increase in carbon dioxide. This work is documented in Manabe and Welderald 1967 paper, and it is noted as the most influential paper in climate science and a seminal work in atmospheric signatures of global warming. So, reading from the article from Schmidt again, it's been called the most influential paper in climate science. In it, they describe for the first time the impacts of increasing carbon dioxide in a radiative convective model that captured the fundamental aspect of atmospheric thought to in a vertical column. Notably, it predicted the right amount of warming at the surface, recognized the troposphere would warm, and predicted the change of the tropopause, and quite non-intuitively predicted the cooling of the stratosphere. Anyway, with that long introduction, Dr. Manabe, Suki, can you give us a perspective on the science of the time in the 1960s that led to this work? How did the community recognize did it recognize the profound importance, or did it take some years to appreciate the work? Suki.
Following the pioneering study of Arrhenius, published at the end of the 19th century, several studies has been made estimating the magnitude of temperature change in response to the increase in the atmospheric concentration of carbon dioxide. However, large uncertainty still remains when in mid-1960s, when our study was published. It took few more decades before the community began to recognize the implication of our study.
Very good. Thank you, Suki.
Yeah.
Next question. Moving more toward the style of climate science. Many of the questions of climate science can only be answered by concerted efforts of interdisciplinary teams and scientists and engineers, such as those who are part of the Geophysical Fluid Dynamics Laboratory, where you spent 40 years of your research career. On the other hand, many questions can be best answered by one or two individuals probing fundamental theoretical questions at the core of the science, such as what you did with Welderald in your 67 paper. Can you comment on the role of large team-based, mission-oriented science projects versus more individual-based research? Do they serve two sides of the same coin? Is it useful for climate scientists to have exposure to both types of approaches in their careers?
In order to construct a comprehensive climate model that has become indispensable for predicting climate change, it is necessary for scientists with different expertise and background to closely collaborate with each other, as we have done at GFDL during the last several decades. In the early 1960s, when early versions of the climate models were developed at our laboratory, electronic computer was very early stage of development. This is an important reason why the parameterization of subgrid scale process in our model were made as simple as possible. Nevertheless, it was very encouraging that these models successfully simulated many salient features of general circulation of atmosphere and the global distribution of temperature and precipitation. Owing partly to the simplicity of parameterization and low computational resolution, the computational requirements of these models are much, much smaller than the current climate model that are used for predicting climate change. Thus, it has been possible to conduct many numerical experiments, changing one factor at a time, using the model as virtual laboratory for exploring inner working of climate system. In fact, the simplicity of the parameterization has facilitated greatly the diagnostic analysis of the result obtained. For these reasons, climate model with relatively simple parameterization has been and are likely to remain very powerful tool for understanding climatic change of not only the industrial present, but also the geological past.
Thank you for that very, very insightful answer, Suki. Next question.
Yeah.
The Nobel Prize is awarded to you in physics this year. This is a clear recognition that climate science is a rigorous science discipline whose predictions made many decades ago by you and others have now become unequivocally measured. Many across the climate science community celebrate this prize and feel some sense of shared achievement. It really is it's a really amazing feat and symbol of the work that a big community of scientists has accomplished. Do you have any advice, Suki, for early career scientists hoping to pursue work that has relevance and impact? For example, what has been the basic driver of your science endeavors? Such things as curiosity, impact, fun, other elements. What is it that drives you and has driven you in the past?
I recommend that the early career scientists to choose the research topics that satisfy his or her curiosity. I also recommend to do things that you are good at doing. Throughout my long career, I have had a great time unraveling the secret of climate change using climate models.
And if I might add to that, there's an element of deep curiosity that Suki has conveyed to all of the scientists that he's worked with, myself included, and it's just a joy to appreciate and to watch the energy and the excitement that Suki approaches the science. So following up on that, Suki, what are some of the current questions about climate science that intrigue you today? Such questions in climate science involve paleoclimate, ocean circulation, tropical storms. You've done a bit of all of those. I'd like to just hear a bit of the words of things that you continue to think about in your work today, which is ongoing. You're still doing work, which is quite amazing.
Here, I would like to list a few of questions that has intrigued me very much. The first question concerns Greenland ice sheet. My question is, are Greenland ice sheet going to disintegrate in near future? That's my question. And using some of the coupled atmosphere ocean ice sheet model, they try to estimate how rapidly Greenland ice sheet disappears as global warming continues. And some models indicate it may disappear in only a few centuries. Another model say it may take several centuries. And as you know, you can imagine to model the continental ice sheet is not easy. But we have to answer this question, how we do it. And probably you can never build a perfect ice sheet model. However, you can monitor how ice sheet is changing, how height of Greenland ice sheet is continuously through remote sensing from satellite, for example. And then check a model against the observation, and then adjust your parameterization, and thereby sort of proceed forward. And that is the approach I am proposing. But this is one of these fascinating questions. Now, another question, second question, concerns the carbon cycle. My question is, when does the ocean stop absorbing carbon dioxide? Running out of carbonate ions. And as you know, that's my question. Now, as you know, the ocean has been absorbing major fraction of carbon dioxide, which we emit into the atmosphere through industrial activities. And however, recently we begin to find ocean is slowing down the absorbing carbon dioxide, as indicated by if you measure the pH of the ocean, and you can see that ocean is slowing down, absorbing carbon dioxide. And so I think this is a really important question in future as we keep emitting more and more carbon dioxide in the atmosphere, and how much ocean can absorb it. And this involves the exchange of carbon between upper part of the ocean and deeper part of the ocean. And this is another very challenging, but still very intriguing question. Now, third question I would like to ask is concerning about glacial and interglacial transition of climate. My question is, why was the atmospheric concentration of carbon dioxide was lower at last glacial maximum, thereby maintaining cold climate of an ice age. Now, if you measure the uh, uh, measure the CO2 contents of air trapped in the Antarctic ice sheet, you can find that CO2 concentration of atmosphere is only 2/3 of the CO2 concentration at pre-industrial time. And why this is happening, my opinion is that ocean, somehow ice age ocean is so cold, can sequester much more carbon dioxide in the deeper part of the ocean, thereby reducing the amount of carbon remaining in the atmosphere. And so that in order to answer this question, you have to understand how ocean mix the, what is the contribution of ocean in the exchanging various material between upper layer of the ocean and deeper layer of the ocean, and thereby reducing the atmospheric concentration of carbon dioxide. And this is a fascinating problem. We have to really understand the how ocean and atmosphere couple with each other and share carbon between ocean and atmosphere. And these are the only 3 examples of very intriguing and very challenging question. I can come up with countless number of these questions and indicating how exciting climate science is. And I hope that you enjoy great time to try to answer some of these fascinating questions, intriguing questions, and have a great time in future. I'm kind of old, 90 years old. So I hope you enjoy very much exploring secret of climate change. Thank you.
Thank you, Suki. That's amazing answer to just inspire lots of future generations of scientists to continue taking your lead on some of these questions. I'd like to close by saying that reading a little bit more about the present times and where we are at with climate science. Clearly, this Nobel Prize is a major scientific achievement, and it is something that comes after decades of research, as Suki has indicated. Both Suki and Klaus Hasselmann are in their 90s and did a lot of their work in the 60s, 70s, and 80s, and into the 1990s. With current rates of climate change, which is about 0.2 degrees Celsius per decade, an assessment of global warming is something that, in a Nobel Prize in global warming, is something that is really long overdue, arguably. And as Gavin Schmidt indicated in his essay in Scientific American, we're basically at a 5 or 6 sigma detection of global warming. So it's kind of at the level of 1 in a billion chance that this is not an anthropogenic signal or that it's not a global warming signal. So I think that the Nobel Committee probably said, look, it's about time, the signal is there, and these great pioneers that did the work in the early days are really, it's time to acknowledge them, just like they do in other areas of physics, like the Higgs boson and the gravitational wave detections. So I really appreciate your time, Suki, and want to offer you one more opportunity if you have any closing comments. Otherwise, we can say goodbye. Do you have any closing remarks in regards to anything else you'd like to say?
Yeah, I think that uh, I have studied uh, exploring the how climate works and how climate is going to change in future. And I think uh, this is a very interesting topics of research, as you can see,
Yeah.
because you have much more computer now available than it was before. And also, you have a massive amount of data from not only in situ observation. We can observe the atmosphere not only with radio sound, but also from satellite observation of sea surface temperature. They even measure microwave satellite, how much rain is falling, or how much water droplet suspended in the air, so that they can know the global rate of precipitation. And ocean observation. In old days, you have a sort of traditional way of measuring temperature and salinity and so forth. But now, you have many thousand of ocean buoys floating up and down, at least top 2 kilometers of the ocean, measuring not only temperature, salinity, but also oxygen concentration. They measure all these relevant variables, many of very relevant variables, which is important, chemical variable, so that you know how the ocean is burping carbon dioxide in the air. And these, we get blessed with beautiful observation of this planet. And in addition, meteorologists can use what you call reanalysis data, the weather forecasting data, which is the data which is used for weather forecasting last 60 years. And then they actually try to predict every day's prediction again using all these data. And we have 60 years of this data available, studying these things. So young scientists and climate scientists has a great opportunity to explore the planet using all these resources, and can enjoy unraveling the secret of climate change. And so I hope that you will really enjoy this great challenge and opportunity in future.
Thank you so much, Suki, for your inspiration and for your words, your amazing answers to these questions. With that, I'd like to say goodbye and thank you again.